Today we are going to present about estimations of obesity levels based on eating habits and physical condition. This data analysis reported to Ajahn Kris. The topic that we are going to present contain data quality investigation, univariate analysis, and multivariate analysis. Missing value. We use the formula count blank, using this function to count missing value in each column, and the result there is no missing value. The rationale from the original database is confirmed that there has no missing value. Duplicate records. Similarity does not equal to duplication. The result is no evidence of redundancy, no duplicate records. Rationale. There is no additional metadata such as timestamp and user ID to confirm recurrence. There is no evidence to support the presence of duplicate records. Without a temporal or entity-specific key, we cannot infer that these records represent repeated observations of the same entity.
For the topic of inconsistent format in the data quality investigation, the results show me that we don't have the inconsistent format, and this is how to check. We start by select the full data range and applying a filter by clicking the filter option under the data tab. This will add drop-down arrows to each header, and then for each column use the filter to identify inconsistent or incorrect values such as misspellings, variations in capitalization, or formatting issues. Filter these values one by one and replace them with the correct, consistent format, either manually or using tools like find and replace, and repeat this process for all relevant columns to ensure clean, standardized data throughout the dataset. So for the topic of outlier, we find the outliers of that database of age, height, and weight. That the result gonna show that we have the outlier of age 168, height we have 1, and weight we have 1. So the first thing that we're gonna do is find the value of this thing, including by minimum, maximum, mean, median, first quartile, third quartile, the value of IQR, the lower and the upper. By use this formula that following this like, and then we find outliers by use Excel formula about equal or like this, and the result gonna show that if it is false, it's not the outlier, but it's true, it's the outlier. And the last thing that we do, we check the amount of this outlier by use formula of equal count if count the amount of true. The invalid or unreasonable values, the results show that we don't have the value of invalid or unreasonable. So to ensure data validity, we can use Excel built-in error checking features which automatically detects common data issues using preset rules when no errors indicators are present, such as for chart or column width or formatting problems, as well as sharp N or A for missing values or sharp no for invalid reference. It suggests that the dataset is free from typical entry errors. This absence of warning signs help confirm that the values are valid, formatted correctly, and reasonable for further analysis.
Encoding categorical variable. This is the data preprocessing step. Ordinal encoding consists of converting categorical data into numeric data by assigning a unique integer to each category. The rationale that we have to do this is that most machine learning algorithms work with numbers and not with text or categorical. And here the example of our work, we turn yes, no into 1 and 0. And we turn the frequently like no, sometimes, frequently, and always to be 0, 1, 2, and 3. Multivariate. We create this by using the Excel and we select data from the top bar menu and then select data analysis on the right hand corner, and then we select correlations. Then we define the data range and output, and the program will evaluate the correlations coefficients. And here is the result. The first one that I see is the negative link between physical activity and obesity. R is equal to minus 0.07279. The pattern is more physical activity means the lower obesity level. These correlations align with common health understanding. The second is eating habits show positive trends. High calorie food are equal to 0.14859 and main meal R is equal to 0.12673. The pattern is bad eating behavior are mildly associated with higher obesity. This is going up together by the habit and the obesity level. These weak but consistent positive trends suggest that poor dietary may increase obesity, even if the correlation is not strong. Family history has some predictive value. Family history and obesity level R is equal to 0.0893. Our pattern is a slight positive correlation. People with overweight in the family tend to have higher obesity score. This reflects genetic and environmental influences. Even though the correlation is not strong, it hints at underlying risks not explained by behavior alone. And next is low correlation across most other pairs. Many variables such as drinking alcohol, transportation, and technology use show very low or negligible correlations. Implication: not all lifestyle factors are meaningfully tied to obesity or each other, at least not in a linear way.
For the multivariate of contingency table, a contingency table, also known as a cost tabulation or cost tab, is a type of table used in data analytics to display the frequencies distributions of the variable. It's most commonly used to analyze the relationship between two category variables. As you can see the table at the left, the table shows the number of the alcohol drinkers by gender and smoking status, and also display each type of the obesity. So I will give a example to you that how to read the table at the table. At the female, we have the total of female 885 divided into insufficient weight for 183 people, and separate to non-smoking 181, and smoking just 2 people, like this that you can see.
This is the univariate, and the first variable that we are going to look into is age. The distribution pattern is heavily right-skewed. Most of data is contracted in 21st to 30 age range. It's about 54% of total. After the age of 30, the frequency drops sharply, and very few people are older than 40. The line chart also shows a sharp peak at 21 to 30 and a steep decline afterward. For the common value and statistics summary, the most frequent value is about 18 years. Median in the middle value is 23 years old, and mean its average age is about 24.31 years old. For first quartile, it's 19.95, Q2 22.78, and third quartile is 26. And the total sample size is 2,111 individuals. So the common age range is between 18 and 26 years. As you can see the unusual pattern, very few individuals aged above 40 is almost negligible beyond 50. An outlier could be those in the 60 to 70 age range because it has only one person. The distribution drops so fast after 30 that it looks like a cliff. That's not typical for many datasets unless there are strong age cutoff. Next variable is wage. Distribution pattern is school left, negatively skewed. Most of the data fall in the range of 31 to 130. The frequency peak in the range of 71 to 100 weight range. It's about 753 individuals. The frequently decline sharply as weight increase beyond 100. The line chart in the first image shows a sharp peak and then steady drop off. For the common value and statistics summary, most common weight are between 71 to 100 kg, and most is about 18, which falls within the same popular range that it makes sense. Median is equal to 83, also in that 71 to 100 range, and the mean is about 87, close to the median, meaning the data isn't heavily skewed, just slightly. And most individuals have weight between 80 to 87 kg, that's slightly pulling the mean upward. And for the unusual pattern, there is an extreme outlier at the higher end. Weight is up to 173, which is the maximum value. But very few individuals are this heavy. Only 2 individuals in the range of 161 to 190. And relative frequency at the high end is near 0%. That's confirming that extremely high weights are rare.
In the univariate of high, the high data shows a rolly bell-shaped distribution with a slight left skew, peaking in the 1.61 to 1.7 meters range, which accounts for 36% of the data. Most values, about 87%, fall between 1.61 and 1.8 meters, indicating a strong central tendency. Out of 2,111 observations, the mode is 1.7 and the mean is 1.7 or 1.7. The reported median of 2 appears to be a data entry error, as it matches the maximum high. The quartiles: first quartile at 1.63, second quartile around 1.7, and third quartile at 1.768. Further confirm that most individuals are rather near the average high, although no extreme anomalies are present. A few cases fall in the lowest 1.41 to 1.5 met and highest 1.91 to 2 met range, suggesting possible outlier or lag high variation. Further, our last slide is univariate of obesity level. The obesity level data show a unimodal and slightly symmetrical distribution, peaking at obesity type 1, which is the most common category with 16.63% of the cases. Most values are started between overweight level 1 and obesity type 3, reflecting a light skew trend toward higher obesity levels. Out of the 2,111 observations, frequencies range from 12.88% for the insufficient weight to 16.63% of the obesity type 1. Cumulatively, 58% of the individual for at or below obesity type 1 and 85% for below obesity type 3, suggesting moderate obesity is more common than extreme cases. While there are no sharp outlier, obesity type 3 is relatively high at 324 cases or 50.35%, which may point to a notable percent of the severe obesity that could require further attention. Thank you so much for keep attention and watching us. The name of member along with dislike as well. So thank you so much.